In this video, I want to look at the so-called extension of the completeness axiom, which is stated in front of you. It is Theorem 84 in our textbook, and it reads, let S be a subset of the real numbers that is bounded below. Then the infimum of S exists and is unique. Now, it is important to understand that our authors have an implicit hypothesis in all of these kinds of theorems, and the implicit hypothesis is that the sets in question are not empty unless you are told that they might be empty. So we are going to assume that S is a non-empty set of the real numbers. And our goal is to show that if S is a subset of the real numbers, S is not empty, and S is bounded below, then the infimum of S actually does exist. We have previously seen that if the infimum exists, it is unique, so we're not going to worry too much about that particular thing. Well, how is this proof going to work? Well, we're going to first of all say that B be a lower bound for the set S. Now, what does that mean? That means I know that B is less than or equal to S for all S's inside set S. And now what I want to do is I want to multiply this inequality that's sitting here in front of us by -1. And I know what that does to inequalities. That says minus B is bigger than or equal to minus S for every S inside set S. And now what I'm going to do is I'm going to define a new set. I'm going to let T be the set minus S. In other words, T is the set of -1 times S, where S lives inside set S. And if I think about this statement here, minus S is just a typical element of T, and so I can rewrite that statement as follows. This says minus B is bigger than or equal to little t for all t's inside set T, and this is since T is equal to minus S. And that means little t is equal to a minus S where S itself is inside set S. Now let's look at this particular statement. This statement says set T is bounded above by minus B. And that is something that I want to definitely make note of. So set T is bounded above by the real number minus B. And that means the completeness axiom kicks in. The completeness axiom says that the sup of T exists. And that's an important idea. Now, to finish this off, I also need one more thing. I need to recall the statement of a previous problem that we have had. We had a problem 81, part B, and it said the following thing. If a set has a sup, so if the sup of T exists, and I pick a C that is less than 0, then the infimum of the set C times T is equal to C times the sup of the set T. And we can apply this theorem to set T and set minus S. And hence we can apply it to S. So I'm going to kind of come over here and I'm going to make notes. T is equal to minus S. So -1 times T is equal to minus S. That is equal to positive S. And if I use this theorem, what I find is the following. I know that the infimum of -1 times t will equal -1 times the sup of t. So the infimum of set S is going to be -1 times the sup of t. And this is since S is equal to -1 times t. And then finally, that means that the infimum of S is equal to minus b, not minus b, it's just minus the sup of t. So let me just clean it up. It's minus the sup of t. And that completes the proof that the infimum exists. As I said before, we've already proved that the infimums are unique. There is one more thing that I want to kind of point out in this particular video, and that is the point of this theorem together with the axiom, the completeness axiom itself. If I look at these two things together, what I now know is that if S is bounded above, then I can say that the sup of S exists, and I don't have to worry about justifying it anymore. That would be the completeness axiom. If S is bounded below, then I know that the inf of S exists. That's the theorem that we just proved, and at this point we will no longer be citing that as a reason every single time. And then finally, if S is bounded, meaning it is bounded both above and below, then I know that both the sup and the inf, they both exist. And so that ends what I want to do for this video.